Okay. Now it's being recorded, and today we're going to see the microsequencer. In some companies like AMD, they used to call it Field Programmable Controller, FPC, but it is a standalone microsequencer. Altera Corporation used to call it SAM, standalone microsequencer. It was EPS or SAM 448. That technology was acquired by WSI, Western Science, something like that, semiconductors, WSI, and they call it EPS, programmable sequencer 448, because it had 448 locations of memory. This one has 512, and the implements complex state machines. It used to have a CMOS EEPROM. The latest ones were having electrical E-square PROM, electrical erasable PROM. By PROM, it means programmable read-only memory. 8 conditional inputs, 16 outputs. Each input can be registered or left unregistered using a multiplexer. 512 words by 36 memory, 25 megahertz clock rate, and every instruction was being performed with one machine cycle, because these machines, they work with machine cycles, not clock cycles, machine cycles. And it has 28 instructions: conditional branching, conditional looping, conditional subroutine call, multi-way or multi-way branch. Okay, so what is the block diagram? It is this. The block diagram has a register for the conditional input, and the inputs, the register can be transparent or latch, or in such a way. If it is transparent, the register is not working. If it is latch, it'll store the conditional inputs, and then it can read them at any time. There are two paths for the data. One path, which is this one, it is the address sequencer, the program memory, and the pipeline register. Okay, the address sequencer, it takes care of loading micro instructions into this program memory. So it is selecting the sequence in different ways. And the program memory stores all the instructions that you write. This is where you store the code that you write. And there is a register at the output, which can work in parallel or as a pipeline. And there is a serial shadow register, which allows you to diagnose the internal data, and that way you can test it. Okay, there is a feedback of 20 right here, of 20 pins, 20 bits. So this path allows you to send feedback and allows you to take decisions, to make loops, take constants, okay, data. And the other path, which is this way, is used for the user. It has 16 bits, okay? So this is the simplified block diagram of a microsequencer. And this is the foundation for the machine language and the foundation for a microprocessor, a microcontroller. Okay. This schematic is very generic, but we will see how it works. Okay. These are other details of the different families of devices. The microsequencer comes in this format in 28 pins, 300 mils, 300 mils from here to here. It's like a 0.3 of an inch. And it has a voltage, it has a ground on pin 14. The conditional test inputs are T0 through T5, T6, right there. And there must be a T7, which is right here. Okay. So these are the inputs of this microsequencer. The outputs are known as P0 through P15. So it starts here, P0, P1, P2, P5, 6, 7, 8, 9, 10, 11, 12 through 15. Okay, those are the outputs where the user can take control of them externally. The logic symbols are this. You have this number of inputs, 8 inputs, and 16 outputs. Okay, and it has a reset, a clock. So you need an external clock to control it. A crystal, an external crystal will make it. Okay. Now, these are the pin description, the definitions. What is a clock input? What are the pins 8 through 7, 8 through 15, which are the 8 general purpose control outputs. Okay, they are enabled by this B, the OE, for low impedance. The low bits, P0 through P7, the reset input, and the test conditional inputs. They are internally synchronized with the clock. So allows you the option of individually bypassing the synchronizing registers. Okay. If you don't want to use the clock, the registers, that's okay, that's another option. Now, and this is the functional description. This is the schematic. So to understand how a microprocessor works, as I always say, it's important, very important to know, to understand a microsequencer. Okay, believe me, once you understand this, then when you will see the internal architecture of a microcontroller or microprocessor, then you see how similar they are and you understand how they work. I took this class on these topics at San Diego State a long time ago, in 1989 to be precise. And I was very happy of learning all these topics because then I understood why I was controlling and I was programming the Intel microcontrollers in those days. And then I was using this technology during the 90s, the early 2000s. But it is the foundation of every microprocessor, so we can't skip it because that way we understand how we write the code, how we write the language. Okay. So the heart of any microprocessor or microsequencer, I'm going to put it here in yellow. It is a program counter register. As you can see there, it is called PC register, program counter. The program counter has another block connected to it, which is called PC plus 1. So if PC, let's say, is in memory location 100, PC plus 1 will be automatically in 101 because it is incremented by 1 in nanoseconds immediately. Okay, and it has a purpose. Okay, so every time the program counter, this triangle is a clock. So even when you don't see here the clock pin, every triangle you see there, that means a clock. So there is a clock also here. So this clock, the clock, it starts incrementing the counter, the program counter. And why is it called program? Because it is incrementing the program that it is written here, the program memory, the program data, which is the assembly code. So, and you see this path goes to this multiplexer. This is a multiplexer. So this multiplexer, when this mux selects this PC register on this area, this channel, that means the program memory is incrementing by 1. So it starts with the first instruction on location 0, then location 1, location 2. Every time a clock hits here or clocks the counter, this one starts incrementing and the memory starts sending the data of the instructions that are stored here. And notice that there are 9 bits for this counter, 9 bits to address this program memory. So with 9 bits, you can address from 0 to 511 locations where the code is stored. So now you can see here that we have different outputs from the memory. The memory is divided into 36 locations from 0 to 35. So they have different applications. So 20 of these bits, these 20 bits of the 36 bits, 20, they go through the pipeline register. Now there is a clock here, so when it clocks, the bits are transferred. They go here. And 1 bit is dedicated to control the output enabled. That means the low impedance to make it work. Because if you control the OE, you can connect other microsequencers in parallel. Okay. Now, when these 29 bits, because 1 is dedicated to OE, the other 19 go here. And from those 19, 5 bits go to the instruction, the code. That means with 5 bits, you can control up to 31 different instructions, but we only have 28 instructions. So that's enough. 5 bits, when every time you have an instruction in assembly code, 5 bits of that instruction will go here, and this one will decode those 5 bits into these outputs, because this is a decoder. Where do these outputs go? These are arrows, all these arrows, they go to all the multiplexers, to this multiplexer, this multiplexer, this multiplexer, this multiplexer right here on the top, okay? This multiplexer, and this one. So all these arrows or output lines control the multiplexers to control the data flow. The homework that I'll be asking to all of you watching this video is describe briefly what every box does in this schematic. And I'm lecturing on this, and every time I'm lecturing, I'm telling you what every box is doing. So it's up to you to take notes. And anyway, they are in this data sheet. They are there. You can read them or you can watch my lesson. So these 5 bits decode, control the data flow, because they control all the control lines in the multiplexers. Remember when we saw multiplexers, we saw that they have the selector lines like S0, S1, S2, depending on the number of channels. Like this multiplexer on the top, because it only has, it is a 2-to-1 max, only needs 1 selector channel. Also this one needs 2 selector channels because it has 4 channels, 4 sources. This one has 4 sources, 2 channels, 4 sources, also 2 selector lines. This one, 1 selector line. This one, 1 selector line. Okay. And now from here, 1 bit is dedicated to polarity, to this exclusive OR. And as we saw last time, an exclusive OR allows me to control the polarity if it is true or false, depending on how you're asking in the code. So you can ask if then else. If this condition T0, because I have the inputs here, if T0 is true, then do this, then go to PL, go to this address. Or you can ask if T0 is false, in other words, if not T0, then go to PL, go to this label. So those are conditional branches that I was asking with true logic and with false logic. And that depends only on this exclusive OR gate. So this one changes the logic from true to false or false to true. From those 19 bits, 4 bits are dedicated to control this test max or testing multiplexer. Why? Because this testing multiplexer allows you to test all these T0 to T7. Right here, you see 8 lines, all this, and they go here. Or allows you to test if a condition is 0. That's why right here, there is a 0. And allows you also to test the flip-flop EQ. This flip-flop detects if this branch control logic is equal to a condition. If this number, let's say, if this number 60 is equal to another code, then enable, then clock this flip-flop, clock it, and I will read if it is equal. If it is equal, that means the condition was true. If it's not equal, the condition was false. Because right here, you might be asking, for example, is a counter, or is these conditions are equal to number 7? Yes, okay, clock this one. And that way, how will you ask for this one? With the multiplexer. And what if they're not equal? Oh, just change the polarity. That way you can change the logic from true to false or false to true. There's another condition that test max will test. It is the 0 box. The 0 box detects if this counter register CREG is equal to 0. Why? Because this counter register controls loops. Every time you're doing a loop, independently of no matter what language you're using, Java, C#, C language, assembly code, okay, machine code, it doesn't matter. When you're making a loop, let's say you want to make a loop 5 times. So you load CREG equal to 5. You load it with this number, okay? Once you load it, then the C minus 1 starts decrementing. 4, 3, 2, 1, 0. When it reaches 0, this one will be clock, will be equal to 1. And you test it here, and this one will take a decision. Okay, you're equal to 0, end the loops. You have to end those loops, okay? And because you know the CREG was equal to 0. Okay. Now you know what is the purpose of CREG, Z minus 1. To create loops, and this one decrements the actual counter. Now, because CREG is an 8-bit counter, you can do up to 256 loops. 255, including 0, 256. Now, when this CREG, no, when this, now we have here, this another. Now we have here a 17 deep stack. This stack is LIFO memory, last input, first output. So the stack allows you to control the number of calls, the number of times you're calling a method or you're invoking a method. In this case, we call them subroutines. So the maximum you can do is 17 nested subroutines, but you can do many calls as long as they're not nested. That's unlimited, of course, depending on your memory, which is 512. But nested calls, which means one inside another, is 17. So you call the first one, call IBC1, and then you perform IBC1 method. And inside IBC1, you call another one, call IBC2, and then in IBC2, you call IBC3. So the stack keeps pushing data. And what is pushing here is pushing the next address, because you need to return to the next address. If you were on line 20, and you call a method in line 100, and you finish in 120, where are you going to return? 21, because you were in line 20, and the program counter jumped to location 100. The program counter needs to know where to return. Who's gonna tell it, oh, return to 21, don't forget. Oh, because the number 20, you were in 20, 21, you see this data path was stored here, right there. So when a return is found, this one pops up the new address, which is number 21. And then this one goes to this new address. And because it goes here, this arrow, the data goes there, and the program counter now gets loaded with location 21. So the program counter never forgets where to return. I always give this example to my student. It's like when you leave home every day, let's say you go to school, in your mind, in your memory, in your brain, you know you have to return. You don't forget where you live, and you know where you have to return. So you have a stack in your brain, and you say, okay, this is my home address, I need to return there. But if you go to a method, you need to return to the next instruction. You can't return to the same instruction. If you return to the same instruction, that will be an endless loop. It'll always be there forever. Okay, now you know why you need the PC+1. It is the next address to return. And who's gonna store it? This one, the stack, the LIFO memory. So the multiplexer, this multiplexer on the top takes care of pushing data, because you can take data from here. You can take data, you see, you can take data from T0 and T7. So you have a binary code here. You see, the binary code goes here through the registers, goes there, and the bits can go here, can go there. And you can load the counter with external data, which we test in inputs, which can be a port, in this case, port T. So this port will load its data to the C register, and that way you can make a loop. Okay, depending on the code, on the number you have here. So now, so we saw what every box does at this time. And the reset can also be registered. Any questions? Any questions so far? So everything is crystal clear. If you have a question, let me know. I have a question. Okay, good. everything is crystal clear. So when I ask, is that clear? All of you will answer, crystal. Not crystal? Okay, tell me what do you need? I don't mind if Ruben ask me questions. Ask me about anything right here, and I will clarify. Remember, I'm here to clarify your questions. Okay, good. That's good. So and anyway, you can read everything that I said. It's here where it says address control logic. That's where it is. Everything is there. Okay, you can read everything, but I prefer to explain it to you in the schematic, because sometimes when you read all these, you don't imagine what is happening. And the best way I learn is by using blocks. When probably most of you see a block diagram, how data flows, then you understand it. But if you just see lots of theory, like it is in this document, you might be confused. Remember when I was telling you the LIFO memory, the stack location, it is pushing the instructions, the return addresses every time you're invoking a routine. That's the way it's being pushed. So when a push instruction is performed, the first location that you were calling is pushed to the second location, is pushed to the third, to the fourth, to the fifth. So the LIFO memory starts getting full, the stack memory. And number two goes here, number two goes here. And so, and these are the latest, the new addresses you're calling. So every time you're calling, the LIFO memory needs to know where to return. Because if you don't store the returns, it's like, it'll be a crash. It's like sending your kids to school and erasing their brain, and you don't know where you live. So get out of here. You know what will happen at 3 p.m. They will not know where to return because you never gave them their return address. So these are the return addresses that are being stored. And then they push back, they pop up, they go up, and they start returning to the correct address. You can read all that. Oh, these are the pops that I said. Now, what happens to the pop? Read it. Okay, 19 goes 18, 17, 16. You see? Okay. What is the purpose of the counter? What is the purpose of the go-to instruction? Go-to, it's a branch control logic. Conditional code selection logic. Instruction decode, operational modes. In the memory, in the program memory, let me tell you where. Right here. Oh, no, right here. In this one. Program memory, in that area, you see the 36 bits from 0 to 35? Let's see how they are arranged, those bits. Right here. You see the 36 bits from 0 to 35. The user-defined outputs, 16 bits, those are your outputs. You can control external devices, hard drives, memories, whatever you want to control. CDs, flash memories, any external device from a computer. So the general instruction format is this. The 0 to 15 location or bits 0 through 15, they are defined by the user. That's control data. Bits 16 to 24 are data. data that you place there. Bits 25 to 28 are for testing, and they are explained right here. Right there. If they are 0, all those 4 bits, you're testing T0. If the location there is 1, you're testing T1. So you say, if T1 is true, oh, you have to put number 1 there because you're testing T1. And pol is a polarity, a 1-bit test condition polarity select. So if it is 0, you are testing if T0, if T1, if T2, if T3, if T5, if T7. Okay, but if pol is 1, you're testing in the opposite polarity, false condition. So if not T0, if not T1, if not T4, is because you are placing a logic 1 there. You see, you change the positive logic, true logic, to false logic. Now, if you want to test if the EQ block, remember the EQ box, the flip-flop EQ, the one that tells you if 2 numbers are equal, where is that? Right there. Okay, you're testing if this condition is equal to a constant, yes or no. You have to write in these bits number 8, 0001. That's number 8 in binary code. Remember, it is 1, 2, 4, 8. So you have a number 8. So you're testing EQ, you have to write this number. If you want to test, if the counter register is equal to 0, or the counter register, you test it with number 9. So those are for conditional tests. But if you don't want to make any conditional tests, and you want to make all your inputs or all your instructions unconditional, you write numbers 10 through 15. Any number you write from 10 through 15, those are unconditional. So what is an unconditional instruction? Like this. Go to here, or jump there, jump here, read this. That's unconditional. Now, a conditional jump is if T0 is true, or if T1 is true, then jump to this location. That's a condition. So you see, these are the way to test conditional, to make conditional instruction, and this is the way to make unconditional instructions, because it is written right here, right there. They are defined right there. Now, what is the opcode? Opcode is the operational code or machine code. In other processor, we will call it assembly, the assembler code or assembly. Okay, notice how many bits are here. 32, 34, 5 bits. 5 bits are required because we only have 28 instructions. We don't need 6 bits. So 5 bits maximum is 382, 2 to the 6. So right here, all the instructions are stored. The compiler, when you write code in your text and you compile it, the compiler converts your code, your text, into operational code. Okay. Now, the general format instruction change these ones. This one that we just saw, and it is called general instruction format, changes when there is a comparison instruction format. Comparison means that you want to compare a constant with another data. So you want to compare if this constant which is data that you place there, a number. You compare it applying a mask. A mask is made of AND gates to allow you to read only those bits that you want to read, because it is masking the bits that you don't need. And it is allowing the other bits to get into the processor. So a mask is made of AND gates. So if these bits right here through the mask are equal to this constant, then you take a decision. If they are not equal, you also take a decision. Okay, and right here the instruction goes here. So this is only for comparison instructions. When you are comparing if one number, if this number is equal to this number. Okay, the mask allows you to read some bits, not all of them. And that's good, because you know what? All these comparisons are performed or executed in one machine cycle. There's no processor in this world that can make a comparison in one instruction cycle. Not at all. And if I'm wrong, you tell me. But the other micros, they take hundreds of machine cycles to perform a comparison. Not this one. This one makes a comparison in one machine cycle. Now that's why it is a high-speed, a complex high-speed state machine, or microsequencer, the more regular name. Any question? Everything is clear. Yeah, conditions like Java code, correct? Because this is from Ruben. Because in Java, of course, you write conditions, and of course, when you're writing in a code like Java, you don't know what is happening inside in the hardware. But in this class, it's called assembly language and machine organization. So we need to know what's happening in the hardware to understand the assembly language. Next week, we will go into the assembly language, into the processor, into the PIC16F69, which is the one you will be receiving in a couple of weeks. Probably by mid-March, I will give you the hardware, and you will be testing instructions at home. So you will be receiving everything you need. Okay. And this is interesting, because then when you see this, you say, oh, now I understand what is happening inside a computer. I understand how it is comparing. Before, you just had an idea, but you didn't know what was happening inside. And I'm giving you the most important stuff from these things, okay? I don't want to go into details, many hardware details, not just the details that you need. And remember the polarity, the exclusive OR gate that I was talking here. This exclusive OR gate, where it says polarity right there, which is this bit, pol, for the general instruction format. Right here, you don't need a pol. So right here it is pol. If polarity is 0 and 0, the instruction that is being tested, 0, 0 fails. 1, 0. If pol is 1, pass the instruction. If pol is 0, fails. So that depends on how you make the combination. Notice here, when they are different, the instruction pass. When they are equal, the instruction fails. And that's the purpose of the exclusive OR gate. Now here comes the good stuff. But we will see only a few now. We can't see the 28 instructions. We will not work with them. I just need you to to see what machine language is. Okay, don't confuse machine language with assembler language, with macrocode language, or structural languages like Java, C++, C Sharp, Python. No. The way they are, the foundation of all languages is this machine language. Then comes the assembler language. Assembler language, every instruction, macro instruction in assembler language is made of these micro instructions. Okay, so these are known as micro instructions that work with microcycles or machine cycles. Now you know what is the difference between machine language and assembler language. Assembler language is a set. Every instruction in assembler language is made of several machine language instructions or micro instructions. So right here, the most basic instruction, go to PL. In other micros, they call it like the old song from that group, Eddie Van Halen, jump. Jump to PL. So jump or go to that location. If you write it this way, that means it is unconditional. So you can write it like this. Go to this location. That's unconditional. But if you want to write it as a conditional, you just write it complete. If this condition is true, then go to PL, go to this location, do this label. PL is the pipeline location. In other words, it's a label, it's a location in the memory. So you are executing, you are in location 3D, you failed your condition, so you keep going. But then the condition is true. If the condition is true, yes. So go to PL data, jump from this location to location 40, jump, and continue with your code. Continue with your code. You see? This is what happens inside. If the condition is true, then the data in the memory transfer the data to the program counter. That way the program counter will jump to that data. Okay, oh, it's not true, the condition was false. Continue, increment the counter, and transfer the next instruction to the program counter. Okay. So it failed, yeah, so continue from 3D plus 1, 3D plus 1, 3D 1, okay, jump to 3D 1. Now the condition is true, transfer the PL to the program counter, the PL data, and jump to location 40. So the PL data is equal to 40. That's why it jumps exactly to that location. So that's the most basic instruction, jump. Any question? Now, with that description, can you study the rest? Of course you can. Now, next instruction, go to TM. Go to test and the mask. Test times mask. So the instruction fails, you are in location 31. If it is true, okay. If this condition is true, multiply the test inputs by a mask, an internal mask, data mask. And if the result is equal to 10, jump to location 10. If the result is equal to 20, jump to location 20. If the product TM, notice that it's not an arithmetic product. It is a Boolean logic product. It's a mask. If the product of this mask is equal to 40, jump to location 40. If none of these are true, continue with location 32. So this looks, in other processors, they call it a fork because it looks like a fork. You have data flowing here, and you have 4 locations of fork, como un tenedor en español. So you have three jumps and this one. Okay. And it is called fork in other assemblers, in other microsequencers. Signetics used to have a microsequencer, the 8X02, a classic 8X02, 02 from Signetics. It's a classic, you can read it. When I was working in industry, I used to see all those microsequencers in the control boards. So you see, go to TM, go jump to the product of this mask. Oh, this computer. Oh, it happened to me what happened the other day. Are you there, guys? Let me move this. Oh, it is here. Yeah, my machine is getting stuck again. It doesn't allow me to read my data. Okay, anyway, we saw a lot of with these instructions. I'm gonna make a video with the rest of the instructions because you notice how interesting it was that we were learning how the data is flowing. And I don't have anything loaded in my computer. I just have this Acrobat document, but the Acrobat is what is failing. I noticed that. Okay, so just let me amend this. Okay, I didn't notice I have more. Jedrin Clemente, Ruben Gonzalez, Marilyn, Lee Gutierrez. So how do you find this microsequencer? You have the link there for the document in the group. It is there, so you can. What I want to cover is probably 6 to 8 instructions. From the 28, I only want to see 6, the most important ones. Then you will make a summary of those instructions, and you will return that homework a week from now. So that way I will give a chance for other students 6 days to read, to watch this lesson and have time to make their homework. What you will do is you will write down the lecture about what is the description, describing every single box, describing 6 instructions, and then write them down on your notebook, scan them with your cell phone, and you can send them to me. You can upload them in Canvas. I can see them there. If you're not using Canvas, you can email them to me. That way I will keep a record. So that's all I'm asking for all of you today. And I need to stop recording.